Hi, everyone. Hope you can hear me. My name is Gananan Kinney. I go by Gnu. Thank you all for coming today. I really appreciate all the previous presenters who presented some really interesting topics. Um, and so I currently work on the hardware CWE team as well at MITRE, and I'm honored to introduce our speakers for today. So we have Dr. Kumar Manjipudi, who is currently a distinguished security solution and assurance architect at Lattice Semiconductor, um, who will be giving the first talk. And we'll next have Derek go after Dr. Kumar, and we'll probably try and take questions at the end of both presentations. Before we get started, though, I just wanted to add on to what Rich talked about with regards to the addition of hardware. If you're not aware, CAPEC also has a hardware category. CAPEC, I believe it's 515. And there are a lot of interesting attack patterns that are sort of grouped under this category that sort of go into attacking physical hardware and physical computing systems. So if you haven't taken a look, I would encourage you to go take a look at that. And with that, Dr. Kumar, would you like to?
Sure. Thank you, Ganu. Welcome everyone to this post-lunch session. Hopefully everyone is actively listening to the presentation. I don't want to keep it boring. Maybe you can ask some questions if you want. But thank you, Ganu. And thanks for my chair to giving me this opportunity to come to this and summit and present my view of material. And the topic is basically securing hardware with the help of CAPEC. So first forward, before I go into this presentation, regarding the polling. In the polling, there are some domains: security, software, hardware, and so on and so forth. If I were to redesign the poll, I would say all of the above. I mean, that option is not available because I'm that kind of a person who does not work in silos and look at a product, whether no matter it's a security, software, hardware, physical security, supply chain security, anything. That's all of it I cover. So I just with that information, I just want to preset what I'm going to discuss here. Okay. So when it comes to hardware, there are certain unique characteristics of hardware, and the hardware CAPEC, the common attack pattern and enumeration classification, and weaknesses and vulnerabilities are, although the vulnerabilities existed for a while, but the CAPEC and CWEs are like only 2 years old at my tier. And there are certain challenges that why we are here, and I would talk about in the summary slides. But the hardware has some unique properties, and the one of the properties is that every hardware is unique. I mean, every hardware vendor, although it is a network on chip or a network interfacing card, every card that supports the network functionality is uniquely designed and owned, and the whole IP is owned by a company, by its inventor, or by the company that it is productized. So that means there is no the commonality is the functionality, but the behavior and the internals are very, very unique, and mostly it is proprietary. And there are very, very few open sources. I mean, I think this poses a unique challenge, which I'll be dealing with later. And then there are libraries, tools, processes, methodologies that does not exist, and that's why one of the things that CAPEC will solve, is trying to solve, is to organize that information. And in compare and contrast to firmware or in the software world, the hardware is extremely difficult to patch. Any vulnerability in the hardware, just you need to spin a new silicon and IP. Sometimes the workarounds are available in the microcode or firmware, but it's extremely difficult, and that makes it more challenging, and why certain aspects are have to be focused in hardware upfront than in the software. And then, of course, each hardware behaves uniquely. Like, for example, you have memories, different kinds of memories, DRAM, SRAM, and then 3D crosspoint. And then you have, if you look at the flash, there are NAND flash, NOR flash, and one-time programmable fuses and all. So each of these, I call it as IPs, they come with their unique limitations. They have their own limitations, and I have seen every hardware has its own limitations, and attackers go after this. So challenges in security, more so in securing hardware, because because it is harder to fix. It is not. It's more proprietary. It's not open source. All of those pose a unique challenge in securing hardware, because there is not a lot of information available to know what kind of a vulnerability or what kind of an attack pattern can be can this hardware be susceptible to or subjected to, right? So, and once you start, security is often sought as an afterthought process. Hey, I have seen many in my 16 years of experience. Hey, I'm going to tape in my chip in 3 months from now. Can you look at security? I think it's too late to look, or even it is taping in the next month. So can you look at security? I think it's very difficult to fix the issues when you are closing to tape out, because there's a lot of validation that goes into, and for those people who are in hardware, and they know what the pain points are if you have to modify a design or logic here and there to fix certain vulnerabilities that are found. And the threat model analysis and vulnerability detection. So the threat model analysis gives a systematic approach, and you have to identify who the attackers are, and so on and so forth, what assets you want to protect, and so on and so forth, to really detect what vulnerability exists. So there is there's a relation between threat model analysis and vulnerability detection, but then it has to be a systematic approach. It cannot be an ad hoc approach. Yeah, you can start ad hocly, but you do not have the comprehensive modeling of all the threats that this particular IP has. And if you look at it, you have to translate the ecosystem, platform, system level, so on and so forth, and IPs. I mean, a memory by such. If you take a memory, DRAM memory, a memory does not pose any. There's no threat associated with memory until and unless you have put some into critical piece of data, and that has some. So the data comes with the security properties, not the memory properties. But once the data that goes into the memory has security properties, then the memory has to preserve or meet those security properties. So that's how the threat model has to be applied. And I think it's the system interdependencies, a lack of understanding all of this ecosystem platform, and so on and so forth, will really resulting in a lot of attack patterns or limitations that an attacker can take use of. And it's and the last but not least, which is not new to anyone in all the domains, is it's often considered as a single person's or team's job. We have a security person who is looking at it. We have a security team who is penetration testing. I don't think so. This is incorrect, as it takes a village to secure a village. I mean, every developer, every designer, every architect every team member has a specific role to play. Some can contribute to at least minimum, and then there's also a maximum that can be contributed. So it's kind of takes a village to that. Securing in again, this is another slide, a different slice of data. Now I don't have a threat model. I don't know how to do the vulnerability detection. But how do I start looking at the hardware? Okay, here is what I mean. It's like a bottoms-up approach or tops-down approach. So the threat modeling is a tops-down approach, but you can also understand the weaknesses. You can also understand the limitations, and then you take a bottoms-up approach for vulnerability detection as well. As I mentioned, the silos, the domains, what we have mentioned in the poll is a kind of a silo, but I see more silos. I have an architecture silo. Architecture is a silo. Developer is a silo. Penetration testing is a silo, and program management is a silo, and so on and so forth. So there are many silos that exist. Marketing is a silo, and the security will have to cross across these silos to make the product secure end to end. And hardware engineers lack understanding of higher stack limitations. And I have heard about this is very common word. How secure boot? Why should I worry about this XYZ? And I say, okay, no, that's not correct, because a secure boot device can be broken or that has runtime compromises. And then likewise, the higher stack users, the firmware users, or the software architects does not understand or fail to forget the hardware goodness that the products, the hardware provides. Like for example, you can have an execution engine, and it has a memory configuration protection unit, and you have to configure memory protection unit to ensure to use the goodness what it provides. But a lot of times I have seen that they are not going to use MPU, assuming that that attacks cannot happen. But that's not this in the real world. The things go other way.
Just a heads up, Kumar, you have about 4 or so slides left, and you have about 2-3 minutes, if you don't mind.
Sure. So again, let's go to the next slide. And jump to how CAPEC can help. Thank you. So what does CAPEC? No, one more. Yes, please. Thank you. So what does CAPEC offer? CAPEC provides a common attack pattern and enumeration and classification for all the attacks that we have, and we have a major classification called hardware. Within that, it creates the awareness, and it provides a bottoms-up approach to TMA and vulnerability detection. So it has all the goodness baked in. It is just 2 years old, if I say. Then there's a lot that can be going into CAPEC to enhance the information to create awareness, and awareness is the key for securing a product. Yeah. So CAPEC offers 4 categories, or 4 attack pattern trees. I would say CMSD. C is considered as the aggregation of all attack patterns considered for that domain, and then it goes. The D is the low-level detail that you can get about the attack flow, and a particular thing is that. So you have wealth of information that is organized in mega attack pattern, standard attack pattern, and detailed attack pattern. So each of these patterns gives you a very good information about where the weaknesses could be and where you have to focus if you have a particular component. Thank you. So the course is it's not well understood because it's proprietary. The information is not publicly shared, and we lack tools and processes. So CAPEC provides a framework, and it opens up the community to reach out or share their experiences, and to ensure the enough knowledge is created, awareness is created, so that the products down the line are secured.
Thank you, Dr. Kumar Manjpuri. That was a very interesting talk. So I heard a lot of the need for being able to communicate, right, and also being able to share these sorts of attacks and information on these attacks. And I also heard there was sort of a need for what level of the hardware these attacks were occurring at. It sounded like so, and I'm sure we'll have a lot more to discuss. So thank you for that. I really appreciate it. Next, I'm honored to introduce Derek Tomorrow, who's a staff engineer at Cloudflare. His focus is on research and development on infrastructure and cloud security.
Thanks for having me. And nice to be able to follow up Kumar. He brought up some really good points on ways of being able to kind of like map these attack patterns, and kind of like how do we as a company kind of like mitigate them. And so this is exciting for me because we build our own hardware, and part of that is understanding what our typical weaknesses are and ways that we can improve it. So discussing some typical ways that we've focused on kind of like securing our hardware, and then kind of what the future holds based off of what we know or kind of like known attack patterns. So this is really important because when we look at firmware, firmware is technically everywhere. I know there's a big discussion whether we consider firmware as being software or hardware, but it's kind of like that bridge between both. And it's important because when we look at where firmware exists, it kind of exists everywhere. Main system firmware, network interface cards, any coprocessors, hard drive, keyboard, embedded controllers, your baseboard management controller, anything out of band, platform controller hub, you name it. All these are unique pieces of firmware that are unique to the system, usually vendor supported and whatnot. But when I look at firmware and when I look at a typical board, I look at it more from like this. It's evident that as we dive further into a board, you see some well-known firmware vulnerabilities to common components, and we can only see how they map to different components. I think there's some transitions if you click that are how they map to different known CAPEC attack patterns, such as manipulating state, like next, cache poisoning, functionality misuse, and shared resource manipulation. So these are some well-known vulnerabilities that we know, whether they attack CPU, things like Spectre Meltdown, RAM, row hammer, your hard drives, typical coprocessors, or DMA attacks against your PCIe controllers. And unfortunately, these mitigations to these vulns are usually vendor specified and either provided through patches or in some cases just disabling the features themselves. And as Kumar alluded to, they're really hard to patch at times. So while some of this might be out of control initially, some things that we do control that are easier is kind of like how we boot our system. So we focus on the Unified Extensible Firmware Interface, or UEFI, and kind of like known vulnerabilities. And there have been some known attacks that map under CAPEC 677 with the intention of disabling these specific security measures and attempting to kind of implant themselves, but create by creating rogue partitions, flash partitions, escalation of privileges, or primarily to maintain this level of persistence. Some really well-known exploits that were out there from the hacking team, LoJax, Fault7, Stark, or Quark Matter, with the idea of not just manipulating these system resources, but modifying kind of the first initial boot code that's responsible for booting the system. And by doing so and maintain that level of persistence, you can attempt to compromise your entire boot chain. And you can click, there's a couple of different transitions, but typically this is kind of like the way we boot our system. We usually create a trust anchor. I think click next, there's a few transitions. Yeah, normally we create our trust anchor in within our UEFI firmware, and with secure boot we can establish that trust relationship between the UEFI firmware and the software that it loads. In this case, we're using Pixie bootloaders, chain load scripts, kernel drivers, all the way to the operating system. But the problem is if you taint a UEFI firmware image, you have a tendency of poisoning the entire boot chain. So we made a previous blog post where we started using CPU vendor provided hardware rooted trusts, where in this case we were using an AMD platform secure processor, where we moved our root of trust into hardware, and then allowed us to be able to, even with the complex, public key infrastructure, allowed us to be able to sign our, UEFI firmware images. Any failures due to lack of incorrect signature would result in a CPU lock state and have our system not boot. So it's good for our x86 machines, but we also needed solutions for ARM. So those familiar in the ARM world, is there's this concept of ARM trusted base boot requirements, which was known as the ARM trusted firmware secure boot, primarily architected for cell phones. The infrastructure was fairly complex because it required a unique SKU per customer, per CPU, per generation. The SoC manufacturer had this responsibility for being end-to-end responsible for the signing, required multiple signing authorities, USB trusted fobs, etc. And what was architected for cell phones really didn't scale well for servers. So this shows the typical authentication flow and the credentials used, as well as like location, whether it was set in an eFuse, EEPROM flash, or TPM. But the idea is that at the left it starts with like a root of trust public key hash, and then the signing process all the way to the significant the relevant bootloaders, all the way to bootloader 33, which is usually performs a measurement, and then from there you set your EFI variables and use for your signing process for secure boot, which is good for secure boot, but it really didn't cover UEFI firmware. So covering the UEFI firmware and the signing process, we're allowed to some of the key points in this slide is that the ARM trusted firmware uses a vendor's public key hash that's eFused as a root of trust public key hash, and then from there the UEFI will use a customer public key hash and it's eFused as its hardware root of trust, allowing us to do things like firmware signatures. So the big question still is kind of BMC protection, and this has kind of been covered somewhat with like HP Series 2600 processors, albeit with some limitations. BMC is generally attacked because of highly privileged access to the host. So some of the things and some of the ventures that we've been looking at are not just the innovations that have been done within the ASP series world, but some other vendors that are out there like Chameleon, Xido. What they're doing is they're creating kind of like this platform secure boot independent coprocessor that allows things for like firmware integrity, physically uncallable function-based identity, things like peripheral attestation, as well as key transition. So one of the problems that we have when it comes to things like e-fusing is that we're using one-time programmable fuses. You can't program again. They're usually embedded in SoC. So this concept of e-cycling, allowing us to be able to remove an identity securely in order to be able to transition them to another company or whatnot, allows that capability. But yeah, so those are some of the future ways of being able to kind of like that we're looking at, kind of like how do we mitigate a lot of these common attack patterns in hardware.
Great. Thank you very much, Derek. That was very interesting as well. Learning a lot about the server hardware sort of attacks, right? And I also, it's giving me flashbacks on all the issues that were plaguing TPM back in the day. So there's CAPEC 29, for example, the time of check, time of use kinds of attacks that were, present back in the day. So this was very informative. Thank you. So with that, I think if we have some time, I think we have about 20 minutes, which is pretty good. The next session's at 1:45. So I think we can open it up for some questions for our esteemed presenters.
Remember to raise your hand if you want to ask a question. You can also post something in the chat.
Yeah, I also thanks, Bob. So I also wanted to introduce Bob, who I completely skipped over very rudely. So I want to give Bob Heineman, who's also a member of the Hardware CWE team, who's also going to be moderating the discussion today. I want to give him a chance to introduce himself as well. Go ahead, Bob.
I got to do all that again. So I'm part of the team, and my background's in embedded system security. And so I'm happy to hear from both presenters. I do have a question that I'd like to sort of kick it off. And Kumar, in your presentation, you had highlighted the fact sort of this dichotomy or this chasm between hardware designers and software designers. And so this question is kind of going out to both you and Derek. Could you comment on sort of what do we think that we could do to sort of bridge that gap? And then also for you, Derek, what do you think, as a result of that gap in terms of the work that you're doing with Secure Boot, do you see weaknesses as part of the solutions out there that are a result of that sort of disconnect between the two domains? So Kumar, if you could start, that'd be great.
Oh, thank you, Bob. So I think that's a good question, and over the years, I have been advocating how to fix the gaps between when the hardware and the firmware should interact with each other. I mean, the problem is, I think, first of all, there are a couple of problems here. First of all, people think people work in domains. They don't want to step out of their comfort zone. I'm a hardware engineer. I don't want to understand anything but hardware. But from a security perspective, that doesn't work. I mean, that kind of a mindset doesn't work. So I enlighten them with some weaknesses or vulnerabilities that I find. Hey, here is how your hardware can be used, and show me. And I say it's a firmware can be compromised. Okay, show me how firmware can be compromised, and then I have to give him. I cannot write a. It's extremely costly to write a proof of concept for every vulnerability it's found, but sometimes we have to write some proof of concepts for exploits. But more so, I take the information and then use the common knowledge to enlighten what the issue is and why it is important now than before. And
Yeah, thank
likewise,
you.
it's the same thing on the firmware side. And the firmware side, like for example, a very classic example, every firmware, crypto firmware or any security firmware relies upon certain random numbers. And the random number is a true random number, and it can fail. It either you have an API, hardware, however you call it as, and then you make a call to the random number, and it gives you a random number and a success or a fail. If it is a fail, then you should not consume the random number. But often I see is that the code developer of the random number call does not understand that random number will fail or can fail, and he just consumes blindly the output that is coming in through that. And it could be all zeros if it is a failure. So I think there's the knowledge gap and the limitations, and this is where the biggest problems lies, like lost in translation, I would call it, as when you take the hardware goodness and try to implement in the firmware, and vice versa, everything is lost in the translation.
Right. Thank you, Kumar. Yeah, there's plenty of examples of hardware security services not sort of living up to what they're claiming in terms of services, or there's examples of developers not utilizing the security surface that are underlying hardware. So yeah, very interesting. Derek, it seemed like you had some comments and sort of some viewpoints you wanted to share.
Yeah, I'm laughing because Kumar, like I wish you were a fly on the wall in some of our conversations, because you alluded to a lot of really great points. A lot of times it's being able to calculate kind of like risk, and how do you calculate it properly in kind of like domains that are very unfamiliar to a lot of development teams internally. We only recently started delving more into true hardware security a few years ago, and a lot of it was understanding the underlying architecture of what our systems actually had and what they contained and where they're sourcing it from. Kumar, you brought up a great point about randomness and entropy. There's a long running debate in the Linux community upon where do you trust your source? Do you really trust it in hardware because of worries about back channels and whatnot? So that kind of spurred this debate of like, well, we can't trust that, so we go to traditional sources. So a lot of it is kind of like some of the unknowns, and so allowing us to be able to talk about this and actually map out specific attacks, show proof of concepts. While costly at times, sometimes there's benefit, because that way you can actually calculate what something is, the true value in a specific attack and what's at risk. We're in over 250 different data centers worldwide. So the risk varies between each data center, whether it be a small tier 3 or much larger tier 1. But creating these kind of new risk classifications, risk categories based off of kind of CAPEC attack patterns allows us to be able to create these new risk scores, as far as if this was a new O-Day or new attack pattern that came out, how can we mitigate this? Are we mitigating it traditionally in software, or are there other measures we can do? And we've been looking at the other measurements as well, because now that we can build better hardware and build better boards that allow us to be able to account for these things, we don't have to take away from the compute that our services really thrive on.
Yeah, thank you, Derek. So I'm just going to open it up here to the sort of the audience members. If there's any questions that you have for Kumar or Derek, put them in the chat or raise your hand. I'm sure they're more than excited to sort of answer and listen to the questions that you may bring to the table. Okay, I don't see any hands yet, so people are probably still formulating their questions.
Bob,
there is
I'll put out a request. We noticed that there are some members of the hardware SIG that are listening in, and while a lot of our discussions with the hardware SIG have been more focused on the CWE side of things, I'd put it out to the hardware SIG members, if anyone's willing to weigh in on, how do you handle the distinction? How much is working on CAPEC and classifying and understanding the attacks becoming part of your day-to-day work within your job, whether you're at a manufacturer or a consulting service or a tool vendor? I think that would be interesting to get some insights, especially
and
members of the hardware SIG.
Yeah, and also, even though you can ask questions to the presenters about their presentation, we're also interested in more general questions about hardware and its use, possibly using CAPEC.
So we do have a question here from Todd. Todd's asking, are all firmware attacks an inside job by someone who understands the target well enough? So Kumar or Derek, do you want to, either one of you want to jump in first and comment on that?
I can jump in and comment on what we've seen. We deal with a lot of contractors, obviously, because we have contractors that come out and will do installations, do RMA processes for us, or do some kind of like simple debugging. So as far as them being an insider, they are probably more insider than what our typical employees would be, where some people never really touch their hands on hardware. Those are kind of some of our biggest threats. There's no guarantees on the person that would be there, but they might have some, explicit knowledge of the underlyings of how our systems are built, and at least to the point of being able to troubleshoot. And so, I would say if there's a concern from an insider standpoint, that would be that. But I don't believe that all firmware attacks are. It really depends on the actual attack itself. If there's something that has some kind of remote capabilities, we've seen that typically with vulnerabilities within the BMC. A lot of times they go unpatched. A lot of times there's default user credentials that are used or default certificate authorities. With those being publicly available and with an IPMI network being exposed, then that attack necessarily wouldn't come from the inside. But with some kind of primitive insider knowledge, especially from a contractor standpoint, those are considered a high risk threat for us.
Yeah. So thanks, Derek. And I would like to add upon what he said. I don't think many of these attacks are insider job or something like that. You need to know insides of it. For example, I will tell you, if you are using a DRAM, or if you are using a specific memory, then the limitations are coming from the spec. So all you have to do is go ahead and read the spec and find out what the limitations are. And there is nothing, internally that you could have some more recipe. Maybe you have an elegant way to exploit, but you have a rude way to exploit as well. But looking at the spec, I always start with looking at the specs, whatever the specs are, whether it's internal, external, or even a data sheet that is available out there. And I start my penetration or attack strategy from there.
Yeah, very interesting, guys. So definitely this, I see definitely two different viewpoints. There's the sort of the deep hardware viewpoint that you had presented there, Kumar. I know you talked about you work out all layers of the stack, but you're talking about sort of like physical characteristics of the hardware or the physics that are driving the hardware and violating those physical constraints in some way. And Derek, you were talking about sort of a little bit higher up on the stack, it seemed like, and talked about inside job. And I also could imagine that question is, it could be someone, it's a knowledgeable insider, but also could be someone has access to proprietary information that could be leaked. So that's another aspect of that. So a very interesting insight, guys. Let's see. Do we have any more questions here?
So I just want to add up on that, Bob. What I'm saying is that knowing the insider information will make the attack or the discovery easy, but that doesn't lack of information doesn't make my job harder, but it's still possible to a certain extent. That's what I want to.
Okay, thank you, guys. We do have another question here. We have a question from Peter, and Peter's asking, how confident are you in the firmware verification techniques you use? So Kumar, why don't we start with you, since Derek's answered first last time.
So I think the firmware verification techniques that we have today are the first line of defense. That's how I would take it. Like you do use automatic scanning tools to find the most common problems. But there are certain subtle issues that you can only get to know with inherent or in-depth knowledge of the associated firm engine security, the execution engine. For example, if you are using a RISC-V versus 8051 versus some other Cortex, then you need to know some of the beauty and some of the limitations of those things. But running an automatic static analysis tool, whether it's a commercial or open, can only find you so much. There are logical problems, there are cryptographic problems, there are protocol issues. There are so many issues that your current tools or techniques are just not quite enough to augment everything.
All right, thank you, Kumar. Derek?
Yeah, I agree with that. I think, the validation of firmware is actually something that's very easy. It's cryptographically verified and whatnot. But again, it's still kind of vendor dependent too. So there's a lot that's outside of your hand. There's only so much scanning you can do before, a 0 day is found, and determining what, how vulnerable you would be to that. We're kind of a big fan of going down the open source route. So anytime you have a piece of firmware that can be open source backed, it allows you to have a little bit more control as opposed to doing like things like microcode updates and kind of keeping your fingers crossed that it works. But yeah, it's I think as Kumar said, the tooling that we have for scanning is kind of the first line of defense. But I feel like having that good relationship with your vendors and being able to do some validation and testing on their end anytime a new vuln is found, being part of potentially their NDA process in order to be able to be known, similar like IPO updates from Intel, be known before a vulnerability is disclosed, that you have proper time to patch. I think allows you to kind of like stay a step ahead. But again, you're still at kind of like at the mercy of a vendor to ensure that things are properly patched.
Great, thank you, guys. Peter, do you have any follow-up questions?
Bob, there's a comment from Murthy at 137. I think was an answer to the question about firmware.
Let's see. So let me just read that real quick here. So Murthy put in the comments, I work for Aerospace Corp. My use case, if CAPEC, we are looking at hardware malware instances recorded as we are developing hardware-focused, I guess that's supposed to be DecSecOps, tool suite, and test automation to identify and mitigate hardware malware escapes and hardware designs. Oh, okay. I maybe this is a question that he's answering from someone else in the chat. Murthy, was there? It looked like you were answering. I just want to confirm, Murthy. Were you asking a question? Because I quite didn't parse out a question in that. Okay, so he was answering. Okay, so sorry for that little diversion there.
But just to piggyback on that, since that has come in, I thought I would share some information here.
Okay,
so,
great.
So I think we have this one domain called supply chain, and the supply chain is applicable to hardware, software, firmware, and everything we talk in between. So malware escapes, some transformation of those malwares can be in the hardware, like a Trojans, they call it as. So, there is some kind of a relation between the Trojans and the malware it is being referred here. But I would say that domain should cover some of these concerns that people might have.
Okay, thank you, Kumar. Derek, any follow-up?
Oh man, supply chain, especially in our hardware, is something near and dear to us, and that might maybe for next year or something, because I have a whole another presentation on that. But again, finding ways of being able to detect changes and whatnot, like kind of like maintaining firmware integrity, I think is a big thing, especially when we have devices that are actually built all over the world, shipped, go through VAT, go through different destination ports and whatnot. Having a kind of a common framework for validation, I think is something that is always challenging, especially when you're dealing with disparate vendors and whatnot. I think that would be a great topic for future summits, because I have too many ideas on that one.
So the
ahead,
good thing is that at 2:45 we're going to have Bob Martin talking about supply chain risk. So you don't have to wait for the next summit.
Okay, so we are getting towards the end of our time here. We're at 1:43. I don't see any more questions in the chat. Maybe my colleagues will let me know if I missed anything. But with that, in the last minute here, are there any points or parting statements that you want to make, Kumar or Derek, as we close out this session for the CAPEC Summit?
Yeah, sure. I just rushed through my, I realized I rushed through my slides. There's a lot of information there. It could have been better. but I apologize if I did not cover everything in the slide. But basically, the essence is that CAPEC serves as a tool or organization that's creating the common framework that will help in the long way to ensure hardware security. I mean, that's what I want to close up.
All right, thank you, Kumar. Derek?
And same being said, I think we're always worried about the mitigation aspects, which we focus on a lot. But being able to map it to specific controls allow us to be able to see the bigger picture and not just focusing on one area, but focusing on multiple. And I think we can all take advantage of the material that's out there produced via CAPEC and CWE, and allows us to be able to build a better strategy.
Great. Thank you, Kumar. Thank you, Derek, for your presentations today and your time. And if we have more questions, we'll put them in the chat. And with that, I'll turn it over to Rich.
So thank you, everybody who asked questions, and especially the speakers from the hardware session.